In this class, we'll discuss about superposition of large number of simple harmonic motions of same amplitude and same frequency, uh, superposing on along x-axis, but they have progressively increasing phase. To start with, let us consider the first oscillation to be taken as x1 is equal to a sine omega t, and the second one is taken as x2 is equal to a sine omega t plus delta. Here amplitude of both the oscillations remain same, frequency remains same, but the phase angle increases by delta. And the third oscillation is taken as x3 is equal to a sine omega t plus 2 delta as increment of initial phase in respective oscillations is taken to be delta. In this way, the nth oscillation can be written as xn is equal to a sine omega t plus n minus 1 delta. Now, the resultant of all these oscillations will be given by x is equal to sum xi, that is x1 plus x2 plus x3 up to the nth term xn. Now we can approach the problem along two ways. One is the vector addition method and another is analytical method. Now to start with, vector addition method, in which we will draw the respective oscillation as vectors, where all the vectors has same magnitude, which is taken as a here, but their phase is changing, is being increased by an angle delta. So in this figure, each chord having length a represents the oscillations x1, x2 up to xn, and each chord is inclined to its immediate earlier chord by an angle delta. The first oscillation x1 is depicted by the chord AB here. This one depicts the first oscillation x1 and this one x2. In this way, the last one is representing xn. Resultant of superposition of all the n oscillation is depicted by the chord AC. AC represents the resultant of superposition of all such oscillations. Now, resultant oscillation makes an angle alpha with the first oscillation direction, that is with the direction of AB. Alpha angle it is making. So we have to find out the magnitude and direction of the resultant vector, that is we have to find out the length of vector AC now, and the angle. To find out R and alpha here, we consider the following facts, that is each chord having same length will sustain same angle at the center of the polygon, or we may say that these vectors are showing along the chords of a circle having radius r and having center at O. Now, if respective oscillations differ by an phase angle delta, then the angle subtended by AB and uh, the other oscillations will make angle delta at the center. So the angle subtended by the chord AB at center, that is AOV, is equal to delta. And as there are n oscillations superposing, so the resultant chord AC will sustain an angle n delta at the center. Hence, angle AOC is equal to n delta. Now, to find out magnitude of AC, that is R, we will draw perpendicular from O to AC as well as a perpendicular on AB. The red one is a perpendicular drawn from O to the resultant vector AC, and the blue one is a perpendicular drawn from O to the initial vector AB. Now, as we know, in this polygon, uh, the perpendicular drawn from this center O divides the chord in half as well as it bisects the angle. So this perpendicular, this blue perpendicular, bisects AB into half, and the red perpendicular bisects the resultant vector R into half, and it also bisects the angle. The red one bisects the angle in delta into equal halves, and the blue one bisects the angle delta in equal halves. So from geometry of this figure, we have that this angle is equal to n delta by 2, and if we say the length of OA to be R, then OC also will be equal to R, and as this perpendicular bisect AB at this point into equal halves, so this half portion of AB is equal to R sine delta by 2, and hence AB will be twice R sine delta by 2. So it is written here A is equal to twice R sine delta by 2. Similarly, chord AC can be written as twice R sine n delta by 2, as from this point to this point, which is half the chord length AC, it is equal to R sine n delta by 2. Hence, magnitude of AC, that is R, becomes twice R sine n delta by 2. Hence, eliminating R from these two equations, we get resultant of magnitude of resultant vector AC, that is R, is equal to A into sine n delta by 2 divided by sine delta by 2. Now we have to find out the angle alpha that AC makes with the initial oscillation direction. To find out alpha, we'll take note of the fact that angle OAB is equal to 90 degree minus delta by 2. How it becomes? Because this angle is delta by 2 and this angle is 90 degree. Hence, this angle is 90 degree minus delta by 2. And as this is a isosceles triangle, that is AOB is an isosceles triangle, hence this angle will be equal to this angle, that is it will be 90 degree minus delta by 2. Similarly, the angle OAC, it is equal to 90 degree minus n delta by 2, as this angle is n delta by 2 and this is 90 degree, hence this angle becomes 90 degree minus n delta by 2. So angle OAB is equal to pi by 2 minus delta by 2 and angle OAC equals pi by 2 minus n delta by 2. Hence alpha, that is angle CAB, equals angle OAB minus angle OAC, that is equal to pi by 2 minus delta by 2 minus pi by 2 minus n delta by 2, which equals to n minus 1 delta divided by 2. Thus we get the magnitude as well as direction of the resultant oscillation, and resultant oscillation now becomes R sine omega t plus alpha is equal to A sine n delta by 2 divided by sine delta by 2 sine omega t plus n minus 1 delta divided by 2. Now there are two special cases. One is when number of oscillations superposing becomes very large, that is n tends to infinity, and amplitude of the superposing oscillations become very small, that is A tends to 0, but phase delta increases continuously, then the polygon, this polygon will turns to an arc of a circle as shown here. If the last oscillation is situated here, then the resultant oscillation would be OA. If the tip of the last oscillation be at B, then the resultant oscillation would be depicted by vector OB. And if the tip of the nth vector is at D, then the resultant vector would be given by the diameter of such a circle. And if somehow the end of the nth oscillation coincides with the starting point O, then magnitude of oscillation would be 0. And the second special case is when the successive amplitude of a large number of component vibration decrease slowly and the phase angles increase continuously, then the polygon becomes a spiral and it is called Carnot spiral. It has very much application in the study of Fresnel diffraction. To move on, the analytical method to find out the resultant of superposition of n oscillations whose amplitude are all same, frequency are all same, but uh, initial phase increases in regular steps. To start with, we take the superposing oscillation as before, as x1 is equal to a sine omega t, x2 is equal to a sine omega t plus delta, x3 is equal to a sine omega t plus twice delta, and in this way the nth oscillation is taken as xn is equal to a sine omega t plus n minus 1 delta. So resultant oscillation would be superposition of all such oscillation x1 plus x2 plus up to xn. Now if we segregate out the coefficients of sin omega t and cos omega t, we will find the resultant oscillation will come out to be this one. And we simplify the expression as equals to r sin omega t plus theta, where we have taken r cos theta is equal to a into 1 plus cos delta plus cos 2 delta, and in this way this summation extends up to cos n minus 1 into delta, and r sin theta is taken to be a plus sin delta plus sin 2 delta up to the nth term sin n minus 1 into delta. Now to simplify these expressions, we will take help of complex algebra, where we can write e to the power I phi is equal to cos phi plus I sin phi, and phi here is any arbitrary angle. So cos delta plus cos 2 delta plus the series extending up to the nth term, that is up to cos n minus 1 into delta, can be written as the real part of cos e to the power I delta plus e to the power I 2 delta plus e to the power I 3 delta extending up to the nth term e to the power I n minus 1 delta, and sin delta plus sin 2 delta and up to the nth term sin n minus 1 delta is equal to imaginary part ip stands for imaginary part, rp stands for real part. So imaginary part of e to the power I delta plus e to the power I twice delta extended up to the nth term. Now e to the power I phi plus e to the power I2 phi plus e to the power I3 phi and extending the sum up to the nth term e to the power I n minus 1 phi can be written as e to the power I phi plus e to the power I phi square plus e to the power I phi cube and extending up to the nth term e to the power I phi to the power n minus 1. Now this series, this summation is in this, the term of this series are all in geometric progression with first term e to the power I phi and common ratio is also equals to e to the power I phi. So summation of this series will come out to be in this way. And if we manipulate this expression, we will reach to the final result, which comes to be cos n phi divided by 2 plus I sin n phi divided by 2 sin n minus I divided by 2 into phi divided by sin phi by 2. Separating the real and imaginary part of the above expression, we can write cos phi plus cos 2 phi plus up to the nth term cos n minus 1 phi is equal to cos n phi by 2 into sin n minus 1 by 2 phi over sin phi by 2, and sin phi plus sin 2 phi plus the other intermediate term extending up to the nth term sin n minus 1 into phi can be written as this. So to find out r cos theta and r sin theta, we will take help of this expression and write r cos theta is equal to a into this, which will become, with the use of this expression, it will become like this, and this further simplified to the expression this one. And r sin theta, which is equal to a into sin delta plus sin 2 delta, and the summation extending up to the nth term sin n minus 1 into delta becomes equal to this one. So the resultant or magnitude of the resultant oscillation r become this one, that is a sin n delta by 2 divided by sin delta by 2, and the angle the resultant vector makes with the initial oscillation, that is x1, is given by tan theta is equal to r sin theta by r cos theta, and it comes out to be tan n minus 1 divided by 2 into delta, that is, it implies theta is equal to n minus delta divided by 2. And here we find the resultant vector expression for resultant of the magnitude of the resultant oscillation, and the angle expression for angle comes out to be identical as it is derived in uh, vector polygon vector addition method. Here we get the same result. Now when n is large and delta is small, then we can write theta is nearly equal to n delta divided by 2, because n then becomes much greater than 1, and we can comfortably replace n minus 1 by n, and hence theta by n nearly equals to delta by 2, and r then becomes r is equal to a sin theta divided by sin theta by n. We have replaced this relation here to get this one. This further simplifies to the final expression an sin theta by theta.